We are going to see one more example of a proof by contrapositive. The result we want to prove is the following. We want to show that if A and B are real numbers, then if the product A times B is irrational, then either A or B must be irrational. So let me write this down. So we are saying A, B are real numbers. And then we have the statement that A, B does not belong to the set of rational numbers. And we want to prove that this statement implies that either A does not belong to the set of rational numbers or B does not belong to the set of rational numbers. We can imagine that here we are trying to prove that statement A implies statement B. So if we want to do a proof by contrapositive, what we want to prove is that the negation of the statement B implies the negation of the statement A. So let's write what those negations are. For A, it's quite easy. If we are saying that it's not true that the product is not a rational, what we are saying is that the product is a rational number. Now here for B, if we are saying that either A is not a rational or B is not a rational, the negation of this is that both A and B have to be rational numbers. So A belongs to Q and B belongs to Q at the same time. I want you to pause the video here and make sure that you agree with the negation of statement B. Okay, so if you are fine with that, then what we're trying to prove is that if A is a rational number and B is a rational number as well, then the product AB is a rational number as well. And this statement is much easier to prove than the original one because now that we say that A is a rational number, we can write A on the form P over Q, where P and Q are integers and Q is not zero. And similarly, we can write B as R over S with R and S integers and S different from zero. So now we want to multiply A and B, so we multiply P over Q times R over S, and multiplying fractions is easy and nice. So we get PR in the numerator and QS in the denominator. QS is not zero because Q is not zero and S is not zero, and this is actually the contrapositive of the non-factor law. And the product of integers is an integer, so both the numerator and the denominator are integers, so we prove that the product is a rational number. So this was much easier than working directly with the statements A and B. But by proving that no B implies no A, since this is logically equivalent to A implies B, we prove the result we want.